This talk is with a number of people and colleagues, postdocs and students, and also with Marco Santello and Nikos Zagarakis, that are colleagues in other universities. I'm affiliated with the Centro Piaggio University of Pisa and with the Italian Institute of Technology in Genova. So the talk today is about bodies, but let's start with intelligence. Many things have happened in the recent years, and of course intelligence has made great strides forward. In the Pumas that we used in the 70s and 80s, we had an intelligence of 160 kiloflops, and today this dumbest smartphone has 40,000 that intelligence, 40,000 times that intelligence. So intelligence has made a lot of progress, but robots may beat us at chess, but not at locomotion, for instance. There is a big gap in what robots can do still today. And the difference is in the physical part of robots, definitely. So here is our own, and I have to show that to be fair to others. Also, another domain where human hands, the difference between nature and robotics is huge, is hands. Hands are a topic of great interest to me. Human hands are an example of beauty and simplicity of control in the complexity of the system. Robot hands have been made for many years, and very nice engineering implementations. Here are a few that try to replicate the human hand. In some cases they take completely different paths. But unfortunately, most of these hands have never found their way to real-world applications, neither in industry nor in prosthetics. And the reason is basically that these hands are too complex. Complexity means that they are fragile, they break very often, relatively often, and especially that they are complex to control. So if you have a robot hand, and if you need to write a long program to control the hand, it will take too much time. And if you are in a real-world environment, not in a university where you can ask students, but in an industry, programming time has a lot of cost. So programming a hand to do a simple graphing manipulation can take thousands of lines. That doesn't make sense. Also in prosthetics, this is a great disadvantage because, of course, people want to have a simple control of their hands. So in prosthetics, indeed, the situation is that we have today two separate groups of prostheses. The one that is most used is the very simple hook or some 3-digital grasp that only have one degree of freedom and a rigid grasp. On the other extreme, we have some sophisticated hands, like the ones that are shown here, where the control comes from EMG control, but is typically rather difficult to perform, because you can, for instance, switch the grasp between a pinch grasp or a power grasp, but to do so, you have to give instructions to the hand. In some prototypes, you can type on your cell phone whether you want to have a pinch or a grasp, or in some other prototypes, you do some sequence of co-contractions of the hand to switch the mode of the hand. So the hand will do this or that. And at the end of the day, people that use those processes get very tired because it's not natural. What is amazing about the human hand is that we use the hand, that is a very complex system, without ever thinking about it. We don't pay attention to the hand. We wouldn't be able to talk and do things and think while we use hands otherwise. So intelligence is advanced, but machine intelligence has advanced a lot, but machine motion did not that much. So in the Pumas we had servo motors, and in 2010 we still had servo motors. So I think the real point that is keeping robotics back still today is the physical part, is the body, at least to a large extent. So that's why we are working on making this work better. And if you think of intelligence being there, is AI really there yet? I don't think so. If you believed you could write a program that replicates the brain, and you found endless resources to do that, so where would you stop? Would you stop at the cortex? It would go down, maybe, of course, the spine, and all the connections, and then the musculoskeletal system definitely is part of what you want to simulate. And even the smallest, under a pinhead in your skin, there are receptors that recently have been shown to do some computations already. There was a nice paper by Vincent Hayward recently where he showed that some computation already happens at the level of the neuroreceptors in the skin. So where does the brain really stop? The body is part of the brain, and if you want to do something really intelligent or a real robot in some sense, you have to take that into account. And of course, this is the whole concept of embodied intelligence, which is clearly not new, does not need to be introduced to you here. And these are the classical definition. As for the hands are concerned, I'm very fond of this citation from the ancient Greek philosopher Anaxagoras, who said that the man is the most intelligent of humans because he has hands, in the sense that the brain, the way we know it, because of the way we manipulate objects, because of the way we work on the world with our hands. So hands are important. I use a different and simpler definition for embodied intelligence, which is that the property of a physical system to adapt and interact with its environment to naturally produce the desired function. So it's simply, you have a body, you have an environment, and they together make a function. And I'll come back on this. So the real problem is how to make robots that are soft, yet strong, simple, but also dexterous, and intelligent and practical together. And our approach is to study natural systems and try to understand, not just copycat, but rather distill principles to apply to different embodiments. And this is what I will try to show in this talk. There are a few things that are happening in recent years. As I said, we were stuck until maybe 10 years ago in many regards, but things are happening pretty fast. And I also listened to other talks yesterday, noticing the same fact that we have we got into a faster pace in our field, I think, since a few years. And why is that? There are a few enablers that came into play, and I will see a couple of them. One is the motor control, better understanding in neuroscience and motor control, and soft robotics. So, of course, the muscular system is very different. You saw some videos before from what we have in robotics. The muscular system has a complex mechanism for recruiting fibers and for making its properties of being both elastic and strong at different times. However, there are models for this that abstract and distill this complexity in a simple way. And one that I found very useful, for instance, is this very simple concept of equilibrium point. The Russian School of Motor Control, Bernstein, Feldman, Latache, who used this lambda threshold, introduced this threshold of the tonic stretch reflex, assuming that the central, or pretending that the central control signals change the threshold of activation of alpha motor neurons to afferent signals related to muscle length. So there is this lambda, which is sort of this threshold, that sets, together with an external load, an equilibrium point, which is a combination of muscle length and force that would have been observed if the control process were left given time to reach the equilibrium. So this very simple concept makes for an explanation of how people move their joints and change the stiffness, which is a phenomenon that we observe very often. In our everyday movement, we not only control the position of our limbs, but also control the impedance, the stiffness of our limbs. And this is fundamental when you interact with the environment. And this is done typically through the setting of the lambdas, of the thresholds of the agonist and antagonist muscles. There are at least 2 agonist and antagonist muscles for every joint. So if you do the semi-sum of the lambdas, should be lambdas here, is the reciprocal command, R command, that sets the equilibrium of the joint, while if you do the semi-difference of the lambdas, then you have what they call co-activation command, and this really sets the stiffness. If you now think of doing robots that have a similar body, or to some extent, or a similar capability as the humans do, then you might think that technology is dominating, and we are very far from that. Maybe this is true to some extent, but not necessarily so much. If you look at the bare numbers of efficiency, for instance, a skeletal muscle has a power density of 0.041 watts per gram and 20% maximum efficiency. An electric motor is better than that. It's 0.5 watts per gram and more than 90% efficiency. So we often overestimate this part, but on the other hand, it is true that while motors outperform muscles, humans outperform robots. Transportation cost for a robot is 10 times higher than a human, at least. And the mass to payload ratio is, again, 10 times higher than humans. So it's really how we put together and how we build the system that makes the difference. Maybe, of course, if we have better actuators, that would be even better. But our focus has been to say, okay, let's use basic technology, conventional electromechanical or conventional materials, but let's try to assemble them in a way that make a system that is closer to what nature does. So there has been in the recent years quite some work on evoluting the motors, the conventional servo motors, to something different. So, for instance, from the rigid actuation in the servo motors of the past, many robots now are using series elastic actuators that are robots with an elasticity in series. And in recent years, there has been people working on variable stiffness actuators that can change not only the position but also the impedance. And this is something that we have been active in also. So, for instance, this one is a device that we came up with in the last few years. It is basically a conventional technology that is assembled in a module where you can change the stiffness and the equilibrium point by having 2 inputs that are R and C, exactly like in a muscle. The internals are shown here, are a bit more complicated, but you can see those as a simple agonist-antagonist arrangement here. And if you design the nonlinear springs well enough, you can have characteristics that match those of muscles. And indeed, the control of a simple element like this is very similar to what you have in an agonist-antagonist pair, where you have the semi-sum and semi-difference algorithm here. And if you look at the torque displacement relationship, here are the human muscle displacements from a publication of Feldman, and here are those that you get from this little simple device. That is modular, is low cost, can be used to build more complex robots that have characteristics that are very similar to those of natural muscles. So the idea here was, let's make something that we can use to build robots that have those variable impedance, variable stiffness characteristics of nature, and try to see what we can do with them. Actually, not just what we can do, but these are open source, so everybody can download and make their own at a very reasonable cost, and build their own robots. The idea being that I believe that there are many applications where you would like to have this variable stiffness behavior, this soft robotics behavior, but the killer application probably it's not me that will see what the application is. So I better have it spread around, and many people use it. Maybe dancing or jumping or whatever could be the good application. So those are available on the web. I'd be happy to give you more details. So here are a few animals that you can build with these cubes. An hexapod, legs. This is a little humanoid torso that does operations like inserting a peg in a hole or drumming. They're very dynamic. Of course, these devices are not exceedingly rigid and precise, but they're very dynamic. And they can be very fast, and they're very robust. Here is a snake, and here is a little demo of what stiffness can change. So here is a snake built out of those modules, and here the same control algorithm is applied when the control is set to stiff, and here when it's set to soft. And as you can see, in the soft configuration, the snake passes through an obstacle, while in the stiff configuration it goes faster without obstacles. That makes a lot of sense, of course. Here are legs that are built out of this, and we are now trying, this is very, very recent, we are now trying to use this variable stiffness, this idea to see how you use the variable stiffness in walking. It is apparent that we change our stiffness while we walk in our muscles. It's not the rigid system where you have always the same. And definitely we found, for instance, and it's relatively easy to show, that you want to be stiff in the stance phase of the leg, while in the swing phase of the leg you want to be as soft as possible. So you basically you alternate swing and stance, soft and stiff as possible. And it also gives you more stability if you are softer with the swing leg, and you can save energy because you don't fight the position with in your swing phase. But let me now go back to hands. That will be the main topic of the talk. So again, human hands and robot hands. Robot hands are too complex. We would like to have them simpler and more effective. And we look at human hands, but human hands are human hands are, after all, they are not so simple. There is a myriad of veins. There are many bones, arteries, ligaments, muscles. These are just some numbers. There are 29 major joints. We cannot really say it's a simple system. What is important is that the brain copes with the hand in a very natural way. So what is more interesting is to see how we organize this complexity and how we can do the same with robots. So there has been, in some 15 years ago, an important paper by Marco Santello and Marta Flanders and John Sechting that looked at a very simple experiment, looked at hands grasping or pretending to grasp, more accurately, many different objects, and taking the statistics of the movement of the hand, building a big covariance matrix of what the angles were during these motions for many subjects, and taking the principal component analysis. And as you would expect, the principal component showed that the first two synergies, here are the principal vectors of the covariance matrix, and here are their representation with the hand. The first two synergies explain 84%, and the first three together already more than 90% of the covariance. And if you take the first alone, it's already more than 50%. So, 1 degree of freedom already explains 50% of the covariance of everyday graph. So this is a powerful means of looking at simplifications. So if you thought of building a hand where the number of the complexity is reduced, where the number of motors is reduced to 1 or 2, instead of 19 or 20, as in the articulations that we had, or 40, like the muscles that we have, then probably you would like one motor to actuate this degree in a coordinate way. And if you had 2, you would like to have, if you had 2, you would probably would like to have them coordinate these 2 degrees of freedom and combine them through linear combinations, so I have to get their mixture. Okay, so this is very nice and clean, and you can imagine to have a hand that does this movement. So this is a rather simple geometric description of the motion of the hand. So for instance, here you have the hand that closes according to the first synergy from with a parameter that goes from 0 to 1. If you think now of grasping a real object, that will not work. There are very few objects that would be grasped by this hand. Why? Because if even a sphere, when you get here, you have the first contact between some finger limb and some parts of the hand and the object, then either you stop here or you penetrate the object. So the shape of the object will not conform to the shape of the hand if you only have one synergy. It's too much simplification in some sense. Okay? So actually, this idea of synergies is good for software simulation of hands, but not really for building. And this is the point where we started our work. So, to this idea of synergies, which we thought was very nice, there was something missing, and what was missing was the problem how you generate grasping forces, how do you interact with the environment, really. It should also be considered that those data from Santello that I showed before were made asking subjects to pretend some grasps, not really doing the grasp. Okay. So the idea then came to say, okay, we need a relation between the grasping forces and the grasping postures and the synergies. And human hands are not rigid. And here, soft robotics and the discussion before comes into play. So it's really different. The hands are made of musculoskeletal system, a skin. The object itself may be compliant. So you have an overall compliance. And then if you do the careful analysis of how the system works, well, of course, you need a little mathematics that I will skip here, but those internal forces, the internal forces are those forces that do not participate in, that do not move the object, but basically only help in squeezing more or less so that you avoid slippage, for instance. And you characterize which forces you can control. It turns out that the forces that you can control for interaction are in a subspace that is parameterized by a parameter that we call here delta sigma, but that really can be interpreted as a Helmholtz law. So let me show this in simpler terms. This is the idea of the soft synergy paradigm that we are using and proposing. So the posture, the kinetic synergy model, the geometric description of the motion that I said before, only rules an internal reference representation of the hand configuration. And the higher level control of the hand commands this internal representation within the synergy manifold. I do not really know what happens in the brain. Let me disclaim, I'm a mechanical engineer, so I do not know what the brain does. But in this picture, the central reference would give a position for a nominal position for the hand. And the hand, the real hand, would be attracted to this nominal position. But of course, the real hand also interacts with objects, so objects will repel the hand if the hand is to penetrate it. And the real hand will stop in an equilibrium between this attraction towards the virtual reference that moves in the manifold of synergies and the object forces. Here is again, so this is the virtual hand that would go inside, and here is the real hand that is attracted towards that, but repelled by the object. We did a little experiment. Unfortunately, it's not easy to have data, quantitative data, but I think this is very, very convincing. I like it. So we bought this on Amazon. This is a hologram, poor version of a hologram. So these are two parabolic mirrors. You place an object on the bottom of one of the mirrors, and the top mirror has an opening here. Probably some of you have seen this already. What happens is that because of the reflection, you see an object up here, while there is no object there. But you see it very clearly. So it's just like an hologram. There is nothing there. So here is what happens if you ask a person to grab the object. Let me show it. Let me show that again. Oops. Yeah.
Also, the movement is not there. It really works.
Okay. Yeah. You see? You really go inside. And here are a few more. Let's see. Yeah, a few more cases. Unfortunately, I changed computer recently, and this one is much worse than my previous one. So the computer, the graphic card is really sucks. But you see, so what happens is that people really go inside the object in order to establish the force that they want to establish. And of course, then they are deceived, they realize they have been deceived, and they give up. So, here is another. Here is another visualization. Here is the same synergy that is shown with this wire frame here. It's going inside, and the hand encounters two different objects. So the final, the reference configuration is the same for the hand, but the final equilibrium is different depending on the object. And this is the model that we use. Okay? This is what we call soft synergy model. So it's much simplified in some sense because you only control the low dimensional description of the reference hand, but takes into account the environment variability. Now, the only point now is that you have to build hands, and we started building hands. So here are the design of the joints. We call it bio-aware. I like this a bit better. You have to know, but then you cannot do exactly the same. Articular joints and soft ligaments. So you can have, you have joints that do not really have pins, but they're all on top of each other. And then you have elastic ligaments that allow you to really take away the finger, and then it will snap back in position. And they are assembled in a hand that has 19 degrees of freedom, 5 fingers, rather anthropomorphic. Here is the hand doing some simple manipulation of an object. So you see that the shape of the hand in this case is different from these cases. Sorry about the video's quality. You see that the shape of the hand changes with the object. The hand is controlled by one single motor that sets the synergy reference. All the rest is balanced by the equilibrium with the object. Here are some showing how the hand is robust. Here is a simple operation of grabbing a cap. We are using the same hand on the same object and the same on-off control. It's simply open and close. There is no programming. But if you see, the approach direction is different, and the resulting grasp is also very different. In one case is this, and in one case is that. And this is what I meant body plus environment function. So the hand is designed to follow the principal component of the human hand, also to deform like the human hand, and when it interacts with objects that have been designed for the human hand, it behaves in a similar way, sort of natural. Here is the hand used on a robot that we have built at IIT with Nikos Sagarakis, and that went to the DRC. So this is not really within the topic, but I just want to show it out because it's a big machine. It's 1 meter 90 centimeters, 200 kilograms. It's a big machine that uses these hands. And so here, for instance, you see the hand opening a door, and you can appreciate how the pinky, if it were not soft, would have crushed, right? And here is the same robot doing other tasks. Here is driving a car. That was pretty stupid of the DRC project, of the DRC competition, the DARPA robotics competition, to ask that a robot drives a normal car, why you could have a robot car. That was the task that we were asked. Yeah, the videos are really crappy, sorry. Here is the human use of the soft hand. You can put a soft hand on a handle and then use it. This is terrible. This is worse than ever. I really have to throw that away. You see that the hand can be used by humans with ingenuity to obtain things that are not trivial. That would definitely not be trivial to program, even if you had all the degrees of freedom. You only have 1 degree of freedom here, and the wrist position, of course. But you have a lot of the human intelligence that is used to deform the hand with the environment to prepare for manipulation. And this is really something that I find so intriguing and unfortunately so difficult. Because what humans can do with this hand is, I would be very happy if a robot could do. But how do you reason about that? The grasping problem paradigm is completely changed, if you want. If you have worked in robot grasping, you know that the robot grasping problem is typically, where should I put my thumb, index, middle, pinky, so that I have force closure, form closure, the equilibrium, and so on and so forth. Here you don't have any of these questions. Your rather reason is you have very few degrees of freedom, only 1 plus the wrist. You have to reason, how do I deform the hand so that it gets that shape? It's a completely different problem. So let me go ahead. The hand is very resilient, it's very robust. Here is my Manuel Catalano, who is the real father of the hand, is the only one who is allowed to do this experiments in the lab that he uses he's very proud. But also very delicate. Can pick up strawberries and noodles, annulini, very delicately. And here we are controlling with EMG control. It's also very simple because you only have one motor. So you need one input channel. So it's natural to think of an application to prosthetics. And this is what we have been doing in the last couple of years. We, in collaboration with with the Mayo Clinic and Arizona State University, also in Italy, we have been doing these applications to prosthetics. So let me go a bit forward in this one. So here is the presentation of the hand. So yeah, this is how we put EMGs on the stump. And the video is a little bit, is for general public. So here is how the socket is prepared. And these are the EMGs placed in the socket. And here is the patient doing operations with the hand. This was our first patient. This is a classical test for seeing how good is the prosthesis. So the person then could do ADL, activities of daily living, very well, I would say. He was very happy with the hand. Can cut bread, spread butter, put some marmalade. It's only one EMG channel. It's actually using two EMG channels, two EMG sensors for one channel. You can also use for work, and this is something that made him very happy because being able to go back to work is something that you don't do normally. Here are a few more patients and experiments that we have done. These are at Mayo Clinic with 9 patients. You see, the people can, for instance, pick a coin from a table, which is not obvious. I must say that I was surprised. The first time I saw this was at a fair where we brought the hand, and there was a school, kids of a school that was trying the hand, and they were trying to do these things and picking up coins. That's it. That I didn't expect, but they were so, freely thinking and ingenuous that they started doing, movements with the hand so that they could pick everything. And that really opened my mind, and they say, oh, well, indeed, it is true that when I do things, I use the environment to shape my hand. I never thought of that before, but if you try to pick a coin from here, you certainly don't do this. You do something like this. So you use the environment to shape your hand. And this is what people do normally. Again, this is difficult to think in robotics, how to do this, but it will take time to do this. So there are more of this here, but let me go forward. Here are some results of the hand. Now we are doing analysis of the results with patients, with all the Jebsen, Taylor, the box and blocks, and all the standard data. The conclusion is that subjects learn very quickly this hand, and they get to a state where they are as good as with their traditional hand in 1 or 2 days, which is very encouraging because it shows basically that the hand is naturally encoded in their body schema. is very naturally used. The hand as it is does not have any feedback, does not have any sensor. Again, the point was to make a hand that was as simple as possible to be viable for real-life applications, industry and people with needs. So we thought that simplicity was, key. Simple is not easy, by the way, so it took us much longer to do this than more complicated hands that we had done in the past. But sensing, we had to think about sensing. It's very easy to put a lot of sensors on a hand and make it very complicated, fragile, many wires that will break very soon. And then, it will be nice on your desk, on your lab, for a little while, then get dusty and you forget about it. So we didn't want to do that. So we thought, in some sense, what is the first synergy of sensing? What is the first most important information that you would like to have from a hand? It turns out that people using the hand, if they see the hand, if the hand is in sight, they don't need much. And you can try yourself with the hand. You can do many things just by eyesight control. What happens is that when you have the hand under the table, or when you don't pay attention, you don't want to pay attention to the hand, then some feedback is important. And we found that, the first, so far at least, unfortunately, we do not have this principal component analysis of sensing. That would be wonderful. I think that would be great. Being able to having all the data coming from a hand and then doing the principal component analysis. That's the dream, but you cannot do that. So we found by experiments that the first most important information is the overall grasping force, how much you're squeezing. Not really which finger is pressing more or less, because that you can rely on the hand to distribute the pressure. So we can do that rather simply with an observer of the torque that basically looks at the current in the motor, and with a cuff display here. So basically now patients have a cuff that gives more force on the arm when the hand does more force on the object. And the second is tactile. Again, tactile would be wonderful to have, but it's rather complicated. You might have tactile sensors on the hand, and then you might have peripheral nerve implants, such as some nice work that has been done, is being done currently. But of course, that is maybe in 20 years from now for real applications. In real case, you have to do something simpler. And we found that, for instance, having accelerometers on the fingernails and voice coils to replicate the same accelerations on the stump is very effective. Of course, tactile sensing is touch is very sophisticated sense. And it wants to have hi-fi. You really need a good hi-fi. So if you have a very good pickup from the fingertips, and a very good loudspeaker here, and a very good amplifier, hi-fi quality, and indeed we are using analog to do this, because digital is not easy. It's beyond what... And then you have a really compelling sensation of incipient touch and also of texture. And here are data from a paper that was published in 2014 on transactions on haptics, where we shown that was really working well. Let me go quickly to the final part and some very, very recent work. All that I showed so far is basically work from 1 or 2 years ago. This is very recent. This has been presented in ICRA in Stockholm in May. So this is the dynamic SoftHand or the SoftHand. The idea is that, okay, we would like to have different grasps. We have a hand, but in some cases, the hand is pretty good, but in some cases we would like to have a power grasp, and in some cases we would like to have a pinch grasp. Okay? Now the hand so far only had one grasp. So we would like to have these two different modes. However, we would like to stay simple. And possibly we would like to have only one input channel again. Having more than a couple of agonist-antagonist muscles to control the hand means that the patient has to learn, and it has a steep learning curve, to use two different motions to do two things. And it's much more difficult. And at the end of the day, they get very tired. And as you probably know, there is a huge abandonment ratio of advanced prosthesis because of the tiredness of the person at the end of the day. So we didn't want to have that. So we want more grasps, but still a single motor and a single input EMG channel. How can you do that? So the idea was to have to encode different movement intentions using the dynamic content of the control signals. Basically, when you want we started with the observation that when you want to have a power grasp, you basically do that quickly, while a pinch grasp, you probably pay more attention and you go more slowly. So we say, okay, we would like to have a hand that if you move quickly, will do a power grasp, and if you move slowly, will do a pinch grasp. And then we had to translate that into the physics to embody this idea. And, oops, sorry, it doesn't show well. It shows what is important. So this is the scheme, the conceptual scheme of the SoftHand, the normal SoftHand, that has these trains of pulleys are the reference synergies. It's the ratio determine how the joints move in the reference. And here is the compliance, the softness. So it's soft synergies. In the new device, we also design, of course, both the pulleys and the springs here are designed on purpose. This is not the real implementation. The real implementation is quite different from this. But this is the conceptual implementation, right? Of course, you have to design the pulleys and the springs in such a way as to have exactly that behavior that we want. So it's a design. Here is the new design, where we use not only springs, but also damping elements that are purposefully designed. And you can do that even using the same material that has different elastic and damping characteristics, if you are able to do that material on design, which is not trivial, but we are working on that. Anyway, if you do this, you can do these experiments. So for instance, you have a slow dynamic synergy that closes the hand as a pinch, while if you close it quickly, as in the one below, you will have this closure. And here is again the same. I hope it's shown a bit better. This is already closed, and it's closed like this. And here closes with a pinch grasp. So you can use this. For instance, if you use the precision grasp for this note, this banknote, you have a good grasp. If you use the power grasp, you have a better grasp for the banknote. On the other hand, if you try to get this cutter here with a precision grasp, it would go away. While here you have a good grasp, a good power grasp for this one. Here are a few more. Again, you see the precision grasp for objects such as this, while the power grasp doesn't perform in this case. And here again, cases where the pinch and the power do different grasps on the same object, or when you can do a pinch grasp of a single piece of paper. take it away. And some more demos here to use the new feature here. So, okay, this we thought it was very nice. It's still, ongoing work. It's not as stable as the first one, and we are, looking forward to implement this on real prosthesis. Final, SoftHand 2. SoftHand 2 is, okay, at some point, at this point of the conference, if I finish the conference here, the first questions I get is, okay, nice, when are you going to put the second synergy in the hand? So now the question will be when you are going to put the third synergy, because we have the second. We want to improve, again, the skills without sensibly increasing the complexity. So it's not really doing the second synergy. It's a bit of a trick. Let me say exactly. What normally happens with the hand is that we have one single tendon going from here through all the fingers back to the motor. And the same motor pulls the tendon from both ends. Okay? So the hand closes the way you saw so far. There is friction, and friction is typically undesired. So if you do not pay attention, the hand would close in a way that is not what you planned for. So you have to compensate for friction in the design of the first hand. So it was fight against friction. And then my student, Cosimo della Santina, came up with a good idea of saying, oh, why don't we exploit that? And then his idea was, let's use two motors, one pulling on this side and one pulling on that side. If they pull at the same rate, I will be back to the original situation. But if they pull differentially, then because of friction, either this or that will happen. So now we have, we design also friction. So we design the springs, we design the damping, and we design the friction in the system. This is the friction design. So that you can have the classical closure here, or the novel closure during the differential control of the two motors. This was the best paper at Humanoids 2015. Here is the hand, again with the banknote or the credit card. Those are egregious examples where the SoftHand didn't do so well, because if you handed a banknote, it would just crash, very early. While in this case, you can do better, as you can see. This is the old version, and this is the new version. And you can do some little in-hand manipulation. You see the student here is using a joystick on the back. And this is an important point. So the joystick basically controls the two directions of motion. I abuse sometimes I say the two synergies, but it's an abuse because they are not really the two synergies. And here are, again, some operations where you can use these internal degrees of freedom to pour coffee or open a jar, or, of course, it's Nutella, and the pick a pen. Now, the problem with this is the control. The control is not really. So we're now using a joystick to do the two motions, but only few, the student who designed it and very few other people are able to learn. So you need to learn to control. And this is probably not going to be easy to use for prosthetics. But for robotics, you can program it more carefully. So there are limitations. As you grow in complexity, of course, you get more on one side, but you have less on the other side. So with this one, I would like to close, and thank you for the attention. and I'll be happy to take any questions.
Thank you, Antonio, for this fascinating talk about hands. So we have some time for questions.
Well,
Mark.
Mike, I really like the idea that you showed at the end of having the two motors in order to have more control over the effective friction. And it's an interesting thing, and I say this because we found the same thing on a hand robot climbing walls, that if you have already grasped an object, then having some friction with this long tendon is actually a good thing, because what it does is it allows the contacts right next to the contacts that are right adjacent to the contact point that have the highest load to relax first, and so you get better load sharing. So it's a kind of, because now with two motors you can play the friction both ways. You can use it one way when grasping, and then another way having already grasped and wanting to resist pull-out forces. At least I think that's
It's a good idea. I'll look into that. I didn't think of this, but thanks for the suggestion. Thank you.
I was wondering if, you define the physical components of grasping, so a way of define the physical components of manipulation?
I define principal components as they were defined in that paper. Okay, so because I don't want to get embroiled in the discussion. So if you ask me what should we be looking at, of course, if you do the same principal component, the same procedure on a different set of tasks that you start with, that is not grasping but is manipulation, or tactile exploration, then you would get probably different principal vectors. That is already known, and it's been seen already. If you had all these experiments together and you took the principal components out of that ensemble, then what you would get? I don't believe I have an answer for this. This is a very open debate in the community doing this analysis. We can take this offline if you want. I have my ideas, but they are not very strong. So I think from us, this synergy is more a principle and an inspiration than a really prescriptive model for doing things. And I confess that in some cases, we tweak a little bit the design of this synergy. We do not stick necessarily to the data that were taken some point in some place from some subjects. But if we see that doing the reference motion with the thumb a bit farther down or a bit upper here is better, we do that. We still think that we can, claim that has been inspired, or at least not claim, but we have to acknowledge that we have been inspired by the synergies, although we do not take them as, prescriptions of what to do exactly, because of this uncertainty in the idea.
Nervous systems use a action potential-based population code. What kind of coding scheme do you use to control your actuators?
Oh, the first part.
Yeah.
We start with the... okay, so the inputs for our actuators are R and C. So it's the reference and the co-contraction. And from there on, we have the dynamics and we know how they will behave. Now, how do we control R and C for a task? If that is the question, that is a good question. That is a good question. And I can expand a little bit if I have 1 second here.
Yeah, sure.
Because I didn't mention much of this, but this is something that we are really working on now, and it's taking a lot of... So people have been building soft robots. I call these soft robots, although people tend to... I had recently a reviewer say, oh, these are not soft robots, soft robots are squishy. I say, well, okay, so human bodies are not squishy, and so we cannot say that we are soft. Okay, I take it for soft anyway. So we are building these soft robots, and there is a large community of people building these robots with compliance, let's say. The Walkman, for instance, that we had for DARPA, it was the only one that had compliance in the body. So there is a lot of compliance, which was useful because when we fell, it didn't break up. So it's pretty good. But what we realized was that for controlling the robot, because of the fact that we didn't have much time to think, because the DARPA challenge was we only had 1 year and so on and so forth, basically, I'll come down and do a little walk here. If you control with the soft joints, what will happen is that you will set a position and then we'll go down and then maybe fall. Okay? So, quick and dirty solution was, okay, let's make a controller that avoids bending so that you walk. And then you end up, the controller is not trivial, but you can do, some, tricks or whatever. You end up making a nice soft robot that behaves like a rigid robot. So what? So why did we do that from the start? And this is something that we realized rather recently. So when you have a soft body and you do feed the control, basically you are fighting, you are defeating the purpose. And so I take your point in the sense that this is not the right thing to do. We realize that. People ask me, what did you learn from the DARPA robotics challenge? This we learned. That is the wrong way to control. And feedback has limitation. I mean, to have performance with feedback, you have to have gain. But if you increase the gain, then you're increasing the stiffness de facto. So it's probably a different scheme, and we are now working on learning control and feed-forward control to try to avoid, to stay soft while moving. I don't know if that answered your question, but it was something that...
We still have 2 questions, Tony, and then...
So you mentioned that one of the problems with prosthetics is this sort of load, this sort of cognitive load of using the device. To what extent do people come to automatize the use of the hand so that they don't have to think about it? Are they able to do that? Just to think, I want to grasp that, and then they just grasp without having to concentrate.
Sorry,
Are people able to use the hand now without having to concentrate on what they're doing?
Yeah.
Or are they able to make it so that they just look, I want to grasp that, pick it up?
Yeah, that's a good point. I mean, I would say they use it very naturally. They don't think much. You can do that yourself if you have one of these hands. By the way, the hands are also open source, and you can download and make your own, or have one for they're considerably cheaper than most of the other hands. But it's a good suggestion to try and quantify how much do you think of the hand. I think it's not as natural as your own, of course. If I think of using myself, I have to look at the hand, of course, because I have no proprioception of where the hand is. I have to look at the hand, but the rest is rather natural. So I am not able to quantify this answer. As I said before, most patients were happy with the fact that it fit their schema very naturally.
Okay, so the amount of sophisticated manipulation you get with a single motor is really amazing. But now when you try to get to mimic better the human performance and you start to add motors, do you think you'll end up with 5 motors or more or less?
No, I don't.
Per finger or?
No, I don't think so. I don't think we will go beyond 2.
Because you still can go better.
I hope I'll find something new. I don't
I'm asking
know 1, 2,
whether-
3, 4.
Yeah, but in human, I mean, if you now try use your findings to understand the human performance, what would be the kind of number of manipulated?
Well, that depends very much on what you want to do. So the human hand has has 19, 20 degrees of freedom, depends. So the full span would be described by 19 or 20 principal
But
components.
you do not, as we showed, you do not necessarily control each of them directly, right? You can kind of, although you have them, you don't have to control each of them.
Yeah. But it is a 19-dimensional space, let's say. So the full description in terms of singular vectors would have 19 singular vectors. And if you want to replicate exactly the same dexterity, then you would need all of them. And maybe some pianists do use all of them independently. But if you are happy with what simple worker can do, then probably one or two synergies are okay. Then if you like, it depends very much on what you want to do.
Do you see that question there? Yes?
So, thanks for the fantastic presentation. And I wonder if you have reproduced a human hand or you have done a hand that is even better than a human hand. It had even better properties because from what I remember from other presentations about grasping, that they have made the point how important feedback, sensory feedback was for grasping. That visually, with the human hand, visually it's difficult, I don't know, to grasp an egg without breaking, without having feedback about that. And you see your hand does very well without that. It's because it has embodied some of the reflexes.
I do not know about those results. I would think that if you see that, that's not an easy experiment to do. If you have no, it is easy to remove the tactile feedback from a human hand with anesthesia, but removing the proprioception and the force feedback is not so trivial. And then even if you did that, I think that if you see the hand, I mean, removing that without affecting the motor control, because otherwise, I mean, of course, you anesthetize everything. But I think that visual control would be enough. I would say that it would be enough to control the forces. If you don't see, then probably not. But if you have a reference, I would be happy to see, because I never saw that before.
Okay. Any other question?
Oh.
Less than
Come on. I thought
No, so what I was curious about, if you are in PCA space, you assume orthogonality, and if you define out the synergies along these PCA dimensions, you also assume orthogonality across your synergies. So, what does it really mean in designing of your hand? Because actually, now we're adding the two motors. I don't think you need to talk about orthogonal control space, right? So, is that now not actually making a request back to the biomechanics here to say, well, maybe we shouldn't analyze these synergies in this orthogonal PCA space, but allowing more dependencies and non-linearities among them?
Yeah, you're perfectly right. So PCA are orthogonal, and that is a property that can be useful. So we, in the past, already, even before the SoftHand, we designed a hand that had 4 synergies with 4 motors that were controlling 4 orthogonal subspaces. And because of the orthogonality, we could make them non-interacting. So you could move each of them independently without moving the other one. So it worked nice as as an implementation of this principle, but the hand was this big. So it's not practical.
Okay.
It's not practical. And what we've done here with the second, the SoftHand 2, is not really, as I said, it's an abuse of notation. It's not a synergy. This is just using the friction. So to differentiate motion is much more like what Mark said before than a real second synergy.
Okay, thank you very much, Antonio, for this.